Welcome to the channel. Our today's discussion is regarding speedometer testing procedures for complete motorcycles, scooters, and auto rickshaws, that is, complete vehicles. Prior to watching this video, it is strongly recommended that if you could possibly please watch the video on the subject of prerequisite preparations and protocols for the standard testing procedure for complete vehicles, that is, motorcycles, scooters, and auto rickshaws. Before going into the details, let us quickly go through few definitions. Number one, speedometer. Speedometer is a device on a motorcycle dashboard that displays the speed in terms of kilometers or miles per hour. Number two, speedometer cable. It's a flexible rotating cable, usually a steel wire, that transfers mechanical rotation from the gear drive to the speedometer head located on the dashboard. Gear speedometer, a mechanical gear mechanism located at the front or rear wheel hub or sometimes at the gearbox that picks up the rotation of the wheel and drives the speedometer cable. Usually consists of worm gear or bevel gear. The drive gear teeth are meshed with the wheel axle or sprocket shaft. Tachometer, it measures engine RPM in terms of rotation per minute. This illustration indicates the parts involved in the linkage of this total mechanism. That is gear speedometer, this one, then gear, then speedometer cable, which is connected to speedometer. The working of this linkage is as follows. As a motorcycle moves, either the front wheel, rear wheel, or gearbox output shaft rotates. This rotation turns the speedometer drive gear mounted on the hub or gearbox. As a result, the speedometer cable connected to the gear drive rotates in synchronization with the wheel speed. Thereafter, inside the speedometer, the rotating cable spins a magnet placed near a metallic aluminum cup. Due to magnetic induction, the spinning magnet causes the cup and thus the needle to move. A hairspring resists this movement, allowing the needle to stabilize at a point proportional to the rotational speed, giving a speed reading. The same cable also drives gears inside the speedometer that turn the odometer and trip meter, recording distance traveled either in kilometer or in miles. RPM indicator. For mechanical tachometers, mostly applicable to older models, a separate tachometer cable is connected to the engine crankshaft, camshaft, and works like a speedometer cable. For electronic tachometers, mostly modern motorcycles, they receive electrical signals from the ignition coil or ECU. These signals are processed to calculate engine RPM, and the result is displayed on the needle or digital display. In a nutshell, the speedometer displays the distance in terms of miles or kilometer, and the speed in terms of kilometer per hour or miles per hour. Speedometer cable, it drives speedometer. Gear speedometer, it rotates cable. Tachometer, it shows RPM or revolution per minute. How to conduct speedometer test? When the vehicle is ready, run it through the test course at a specified speed as indicated by the speedometer, and at the same time make an actual speed measurement. The test speed should start with 20 km per hour and increase at the interval of 10 km per hour for each successive. With the result obtained by the actual measurement as stated in number 1, determine the speedometer correction rate. The speedometer correction rate, CV, is equal to V divided by V dash multiplied by 100, where CV is speedometer correction rate, V is actual speed in terms of kilometer per hour, and V dash is speed indicated by the speedometer in terms of kilometer per hour. Speedometer correction rate. Speedometer correction rate shows the percentage ratio of the actual speed to the indicated speed by speedometer and is used to assess how much the speedometer reading deviates from the real speed. Speedometer correction rate is actual speed divided by indicated speed multiplied by 100. Its interpretation is if CV is equal to 100%, the speedometer is accurate. If CV is less than 100%, the speedometer overstated the speed, shows more than actual. If CV is greater than 100%, the speedometer understates the speed, that is showing less speed than the actual. Let us consider this example. Here, the actual speed is 100 km per hour. Indicated speed is 105 km per hour. Therefore, the speedometer correction rate is equal to 95.40% by using this formula. Meaning thereby, the indicated speed is about 4.76% higher than the actual. That is, it is overstated. Coming to speedometer error rate. Speedometer error rate is the percentage difference between the speed indicated on the speedometer and the actual speed. It tells us the percentage deviation of the indicated speed from the actual speed. The formula is E is equal to V dash minus V divided by V multiplied by 100. That is, E is equal to indicated speed minus actual speed divided by actual speed multiplied by 100. Its interpretation is as follows. If E is 0%, the speedometer is accurate. If E is greater than 0%, the speedometer reads faster than actual. If E is less than 0%, the speedometer reads slower than actual. Let us consider an example. Given, if the actual speed is 100 km per hour, indicated speed is 105 km per hour, then error rate is V dash minus V divided by V into 100. That is, error rate is equal to 105 minus 100 divided by 100 into 100 equal to 5%. As discussed before, the interpretation would be as follows. If E is 0%, the speedometer is accurate. If E is greater than 0%, the speedometer reads faster than the actual. If E is less than 0%, the speedometer reads lesser than the actual. So plus 5% mean the error rate is plus 5%, confirming the speedometer speeds by 5%. Let us now move forward to odometer correction rate. Odometer correction rate is a ratio or percentage that shows how much odometer reading, that is indicated distance, differs from the actual distance traveled. How to conduct this test? To start with, one rider move the test motorcycle on the test course so that the speedometer driving wheel rotates several times. Then measure the distance moved and obtain the wheel effective diameter by the following formula. Perform the test at least 3 times and obtain the average value. The formula is the effective diameter is equal to L divided by pi n, where D is wheel effective diameter in meters, L is the distance moved in meters, n is the number of wheel rotations. With the result obtained as specified above, calculate odometer correction rate by the following formula. Correction rate is equal to pi d multiplied by K1 multiplied by K2, whereas D is wheel effective diameter, K1 is distance meter rate, K2 is speed reduction ratio for distance meter driving. K1B can be defined number of speedometer shaft rotations divided by distance indicated by distance meter. K2 is equal to number of wheel rotations divided by number of speedometer shaft rotations. How can we calculate the effective diameter of the wheel? We can calculate, provided if we know how far the vehicle has moved, that is the distance L, and how many times the wheel has rotated, that is number of rotations. We know the circumference of the wheel is equal to pi d, and if the wheel rotates for 1 times, the total distance covered will be pi multiplied by d. If the wheel rotates for n number of rotations, the total distance covered would be pi dn. With this formula, we can come to the conclusion that effective diameter of the wheel is L divided by pi multiplied by n. Coming back to odometer correction rate formula, odometer correction rate is pi d K1 K2. And if we substitute the value of d, that is d is equal to L divided by pi multiplied by n. We get pi into L divided by pi n multiplied by K1, K2. That is, pi and pi gets cancelled out. Therefore, the odometer correction rate comes out to be L, that is the total distance moved, into K1 constant, into K2 constant, divided by number of rotations. Its practical meaning would be that the correction rate depends upon how far the motorcycle has really moved, that is the distance L, and how many times the wheel has rotated, that is number of rotations N, and how the speedometer system converts these movements into the distance on the odometer using constants K1 and K2 factors. Now, how the speedometer systems converts those movements into distance on the odometer. We know odometer does not measure distance directly. It counts mechanical rotations, especially of the speedometer shaft, which is driven by the wheel. The two ratios K1 and K2 explain how wheel movement is mechanically translated into odometer readings. So here is how the conversion happens. The wheel rotates, that is, it drives the gear mechanism. Through gear reduction K2, the wheel rotations turn the speedometer shaft. The speedometer shaft rotations are used to drive the odometer counter, which has its own mechanism for counting K1. What exactly is K1? K1 is odometer rate, which can be expressed by the formula number of speedometer shaft rotations divided by distance indicated by odometer in meters. Meaning thereby, it tells us how many shaft rotations are needed to increase the odometer by 1 meter. This depends upon the internal gear ratio and mechanical setup of the odometer unit. And we can explain by this. Say if K1 is equal to 2.0, the odometer moves 1 meter for every 2 shaft rotations. Higher K1 means more shaft rotations are needed, that is, odometer advances more slowly. Lower K1 means fewer shaft rotations are needed, that is, odometer advances faster. Coming to K2. K2 is a speed reduction ratio for odometer. It can be expressed as K2 is equal to a number of wheel rotations divided by number of speedometer shaft rotations. Meaning thereby, it tells us how many wheel rotations are needed to produce one shaft rotation. This is part of the mechanical link between the wheel and the speedometer or odometer system via gears or cables. We can say that, say if K2 is equal to 0.5, then for every 2 wheel rotation, the shaft rotates once. If K2 is equal to 1, the shaft rotates once per wheel rotation. This gear ratio can vary based on motorcycle design, that is, wheel size, sprocket, gearbox, etc. Who provides K1 and K2? K1 is typically provided by the speedometer odometer manufacturer because it is tied to the internal gearing system of the odometer unit. It may be specified in technical manuals, parts datasheets, or calibration guide, etc. K2 is typically determined by the vehicle manufacturers, since it depends upon the wheel size, gear train from wheel to speedometer cable, gear ratios in the wheel hub or transmission. In practice, vehicle engineers may measure both K1 and K2 during vehicle development or type approval testing. In field calibration, these may be measured manually using test bench, wheel rotation counters, and shaft rotation counters. Summary regarding the constants K1 and K2. K1 is distance meter rate. Its meanings are shaft rotations per 1 meter indicated on odometer. It is provided by speedometer manufacturer. K2 is speed reduction ratio, that is wheel rotations per shaft rotation. It is to be provided by vehicle manufacturer. Let us consider practical example. Suppose the vehicle under test has traveled the distance 1000 meter, that is L. Wheel rotations are N, that is equal to 900. K1 is 2.0. K2 is equal to 0.5. The odometer correction rate will be 1000 multiplied by 2.0 multiplied by 0.5 divided by 900, or 1000 into 1.0 divided by 900, or 1000 divided by 900, that is 1.111. That is, correction factor is 111.11%. Meaning thereby, the odometer is over-reporting the distance by about 11.11%. The motorcycle would need calibration to reduce this overestimation. Odometer correction rate can also be determined by the direct method. The procedure is measure the distance the vehicle has moved, say from point x1 to x2, using GPS coordinates. Measure time using high precision electronic watch or electronic counter. Use the formula to calculate odometer conversion rate. That is, odometer correction rate is equal to actual distance divided by indicated distance multiplied by 100. Summary of today's discussion would be: number 1, speedometer correction rate is equal to actual speed divided by indicated speed multiplied by 100. That is, speedometer accuracy as a percentage. Speedometer error rate. Speedometer error rate is equal to indicated speed minus actual speed divided by actual speed multiplied by 100. It shows Deviation. Positive means over, negative means under. Odometer correction rate. Odometer correction rate is L multiplied by K1 multiplied by K2 divided by N. It determines the odometer accuracy. Our next topic of discussion will be maximum speed test. Stay tuned and don't forget to like, share, and subscribe to receive the similar contents in future too. Thank you. Thank you very much.